In a direct coupling scheme, no resistors are required, no capacitors are required, no inductors are required. Just a pair of wires is more than sufficient to implement this scheme. This scheme couples all the frequencies ranging from DC 0 to infinity from the output of one stage to the input of the next stage. One can easily notice that this is the simplest possible coupling scheme. In inductor coupling or transformer coupling, a transformer is used. Zero frequency or DC is prevented from being coupled from one stage to another. All other frequency components, non-zero frequency components, are allowed to pass from one stage to the next stage when this coupling, transformer coupling, is implemented. This coupling is associated with one benefit, that is, with the help of this scheme, it is possible to couple maximum amount of signal from one stage to the next stage. In RC coupling or capacitor coupling, a circuit consisting of resistors and capacitors is used. This circuit couples frequencies, especially high frequencies. Low frequencies are attenuated and zero frequency or DC is completely blocked. This is somewhat a simpler technique and it occupies less space when compared to transformer coupling. This is the coupling that is widely used in coupling individual stages in a multi-stage amplifier. Multi-stage amplifiers coupling schemes, part 2, series on semiconductor devices and circuits, lecture number 7.11. Coupling schemes pertain to interconnection that exists between two different stages in a multi-stage amplifier. There exist three types of schemes, techniques: RC coupling or capacitor coupling, transformer coupling or inductor coupling, and the last one is direct coupling. Regarding the first two, a discussion has already been done in part 1 of coupling schemes. In this session, we focus on third scheme, that is direct coupling scheme. Here we also focus on how bandwidth gets affected when one goes for multi-stage amplifier design. Usually, multi-stage amplifier gives more gain when compared to single-stage amplifier. What about bandwidth? How bandwidth of a multi-stage amplifier compares with bandwidth of single stage? This aspect also considered in the present session. Now we move to begin the course session. We start the session with a few points regarding DC or direct coupling. This method is often referred to simply as DC, which means direct coupling. It also means direct current. In this scheme, direct current is also transferred, also connected to the next stage from previous stage. So signal plus direct current DC both are provided a path while connecting the output of one stage to the input of the next stage. So DC can mean direct coupling, it can mean direct current too. In this scheme, the output of one stage is connected directly with conductors to the input of the next stage. So in this scheme, no capacitor is required, no transformer is required, only two wires. So that's why it is called simplest coupling scheme. As a consequence, both AC and DC voltages at the output of one stage appear at the input of the next stage. Here is shown two stages which are coupled in a direct way. Here is one stage which employs Q1 transistor, another stage which employs Q2 transistor. These two are connected with a wire. You don't find any capacitor, you don't find any transformer in between them. So it is direct. Coupling is direct. Of course, at the input terminals of the first stage, you can find C1. C1 couples the source to the first stage through a capacitor, C1. So capacitive coupling, RC coupling. C1 implements the RC coupling between source and the first stage. At the output terminals of the second stage, you can find C2. C2 couples output to the load. C2 therefore implements RC coupling between second stage and the load. You can imagine load here, RL. So in this diagram, you can find RC coupling at two places, direct coupling at one place. Some more points regarding DC coupled amplifiers. Widely used DC coupled amplifiers are Darlington pair. Darlington pair is a two-stage amplifier. It uses direct coupling. Those two stages are CC, CC. Darlington is meant for achieving high input impedance and high current gain, mainly to achieve high input impedance. It doesn't have any FET version. Reason is single FET stages are capable of giving as much input impedance as required. So there is no need to go for two-stage FET amplifiers to achieve high input impedance. For this reason, you don't find FET version of Darlington pair. Another example for DC coupled amplifiers is cascode pair. In cascode pair, BJT version, one stage is CE, another stage is CB. In FET version, one stage is CS, another stage is CG. Cascode pair is there to increase bandwidth, to increase highest frequency of operation, or to modify frequency characteristic of the amplifier. Differential pair is also there. This is also an example for DC amplifiers. In differential pair, one can find CE, CA, CS, CS. CE, CA in case of BJT version, CS, CS in case of FET version. These are all examples for direct coupled amplifiers. As already mentioned, these are all two-stage amplifiers. DC has certain advantages. What are they? This coupling involves a simple circuit arrangement. It is quite inexpensive. It is the simplest possible coupling scheme and it is least expensive of the three. Low frequency signals and even DC can be amplified. It is able to provide uniform frequency response up to high frequency. Lower cutoff frequency is 0 and upper cutoff frequency is determined by values of components used. So these are advantages. Simplicity, inexpensiveness, zero cutoff frequency. These are all positive features of direct coupling. Disadvantages are also there. What are they? These amplifiers are associated with gain decrease at high frequencies. Even when input is pure AC, some DC component is present at the output. Another disadvantage. Any noise or stray pickup present at the input is simply passed to the output in an amplified form due to high gain. So noise gets amplified and appears at the output terminals. Change in output voltage, even when there is no change in the input, exists very often. This is called drift and is due to temperature variations, aging of components, etc. These are some of the issues associated with the direct coupling scheme. Some applications of direct coupling technique. It is used in TV receivers, computers, regulator circuits, and electronic instruments. These are all applications. It is also used in the design of differential amplifiers, op-amps. Now, after having some understanding regarding coupling schemes, three coupling schemes, we consider the impact of going for multi-stage amplifiers on the bandwidth. Multi-stage amplifier design increases the gain, but what happens to the bandwidth? Bandwidth is as important as gain to an amplifier. Sometimes it is more important, more significant parameter than gain. Bandwidth is a frequency domain specification. In time domain, it is indicated by rise time. More bandwidth means less rise time. More bandwidth means fast response. Less time, rise time also means same thing, fast response. Now we consider a few points pertaining to bandwidth of multi-stage amplifiers and compare it with the bandwidth of single stage. By cascading several stages together, gain improvement is realized, but at the cost of bandwidth. Gain rises, but bandwidth falls. When several identical and non-interacting stages are cascaded, identical, non-interacting, overall lower cutoff frequency is more than lower cutoff frequency of any one stage, and overall upper cutoff frequency is lower than upper cutoff frequency of any one stage. The net result is shrinkage of bandwidth. What does it mean? Let us suppose this is frequency response of a single stage. This is lower cutoff frequency. This is upper cutoff frequency. This is bandwidth. This is for single stage. Several single stages, similar, identical single stages are used in the design of a multi-stage amplifier. Then that multi-stage amplifier gives a frequency response with FL more than FL of single stage. So FL of multi-stage is going to be somewhere here, higher than FL, and FH lower than FH of single stage. So it will be somewhere here. This is FL, this is FH of multi-stage. So the result is bandwidth shrinkage. So when you go for multi-stage design, multi-stage design is associated with bandwidth shrinkage. It can be shown that the lower and upper 3 dB frequencies for identical non-interacting n-stage cascaded amplifier is given by this formula. FLN means N refers to n-stage amplifier, L lower cutoff frequency. This is lower cutoff frequency of multi-stage amplifier. This is lower cutoff frequency of single stage. So this fellow is more than FL. Now second expression, FHN. This is upper cutoff frequency of multi-stage amplifier. This is for single stage. FHN is lower than FH. From this expression, one can easily notice, one can easily compare the cutoff frequencies of multi-stage amplifier and cutoff frequencies of single-stage amplifier. In a cascade of stages, if the input impedance of one stage is low enough loading the previous stage considerably, then it is no longer possible to consider them as non-interacting stages. So far, we considered lower cutoff frequency, upper cutoff frequency. Just now, we noticed some expressions. Those expressions are derived assuming non-interaction between the stages. Sometimes it is not possible to assume non-interaction between the stages. They become interacting stages. In a multi-stage amplifier system, one stage may be interacting with the next stage. In such case, the formulas we considered just now, they don't work. So when it is not non-interacting stage design, in such case, when the pole frequencies of the overall transfer function are F1, F2, Fn, then the overall upper cutoff frequency can be found from this formula. This is the expression one has to use. 1 over square root of 1 plus Fhn by F1 whole square whole power n, like that. Notice F1, F2, Fn, etc. equal to 1 by root 2. So this expression one has to use to find overall upper cutoff rate. If the pole frequencies F1, F2 are not widely separated, then high 3 dB frequency Fh can be found within 10% accuracy from this relation. 1 by Fh equal to 1.1 square root of 1 by F1 square plus 1 by F2 square plus etc. plus 1 by Fn square. See, the expression that is given in the previous slide, it is quite complex. One may need to go for a digital computer to solve it, to find Fh. Here, right now, you can see a relation for Fh, but it is not exact. It gives a result with an accuracy of 10%. If the cascade has a dominant pole Fd, which is much smaller than all other poles, then Fh is approximately equal to Fd, or high 3 dB frequency equals to dominant pole frequency. So these are all approximations. If you want exact, then you have to use the formula that has been given in the previous slide, and all these things are for a multi-stage amplifier design with interacting stages. It has been mentioned that bandwidth is frequency domain specification. Corresponding parameter in time domain is rise time. More bandwidth refers to less rise time. A few points regarding multi-stage amplifiers. in terms of rise times of individual stages. Let us suppose TR1, TR2, TRN are rise times of isolated individual cascaded stages. If the input waveform rise time is TR0, then the output rise time TR can be found to within 10% as TR is equal to 1.1 square root of TR0 square plus TR1 square plus TR2 square plus etc TRN square. If upon the application of a voltage step, one circuit produces a tilt of P1% and if a second stage gives a tilt of P2%, the effect of cascading these two non-interacting circuits is to produce a tilt of P1 plus P2%. So rise time, tilt time, these are all time domain specifications. They provide information regarding lower cutoff frequency, upper cutoff frequency of the multi-stage amplifiers in time domain. With this, we come to an end to the session. To recollect, in this session, we described direct coupled coupling scheme and then the impact of multi-stage design on bandwidth, on lower cutoff frequency, upper cutoff frequency. These aspects are also discussed. Rise time, tilt, these are all time domain specifications. Impact of multi-stage design is also described in terms of these two time domain parameters. Hope this session is useful to you. We meet again with a new topic very soon in another session.